Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of stellar evolution, and in particular, we're going to concentrate on the ultimate fate of the highest mass stars in our universe. If you recall from the previous videos, when it comes to the process of stellar birth and stellar life and how stars die, the whole process is driven by gravity, and of course, gravity is determined by mass. So we've already talked about what the lowest mass stars in our universe will do when they die, and we've just concluded with what the intermediate mass stars will do. And in this video, we're going to talk about the highest mass stars and what they go through as they end their existence. So let's go ahead and get started. Now, the category of high mass when it comes to stars are stars that are greater than 8 times the mass of the sun. So you'll notice there's no upper limit to this. There's no upper end. And to be quite honest with you, we're just not really sure what is the maximum mass that a star can have. We do know that there are some internal issues that occur for a star that's very massive. If the star is too massive, its energy production will literally blow the star apart and will not be able to be a star. But there are stars out there that are more than 100 times the mass of the sun, and they're able to exist as stars. So we're not really sure what the upper limit is. But what we do know is that a high mass star must be greater than 8 times the mass of the sun for a particular reason, and we'll get to that here in just a second. You'll notice that I'm still using the same pictures that we've seen in the previous videos, and we're recycling these pictures because if you recall, the idea is that the sequence of events that a star goes through really is the same regardless of its mass. Low mass stars, intermediate mass stars, high mass stars will all go through the same various events throughout their lifespan. The main difference, though, is how quickly they do it. And if you remember, the rule is that the higher the mass of a star, the faster it goes through its evolutionary sequence. And so keep that in mind as we go through this as well. A high mass star does everything that all the other stars do. The high mass stars will start off with a mostly hydrogen composition. At their cores, they will convert hydrogen into helium through the fusion process. The hydrogen envelope is something that never gets used, it's just not hot enough. So remember, the envelope is the region surrounding the core, the hydrogen that's just never used. At the end of its main sequence existence, what will happen is the star will develop a helium core. Helium requires a much higher temperature to fuse, and so the core begins to collapse, the core becomes hotter, and if that core can get hot enough, the helium will fuse. Now, when the core collapses and gets smaller, the hotter that the core is getting is forcing the envelope to expand. And so what we saw in a previous video is that the star will eventually get the helium to begin to fuse. And once the temperature is met that is required for helium fusion, the process of fusion produces light, the star stabilizes, but in the meantime, it has blown and sort of bloated itself up into this red giant phase. Now, this is the same thing that an intermediate mass star will do, but the big difference is that a high mass star goes through these stages faster than an intermediate mass star does, and there's also one major difference. When helium fusion occurs at the core, the product of helium fusion is carbon with a little bit of oxygen. And if you remember from the previous video, intermediate mass stars, when they develop a carbon core, they never get that core to become hot enough to get the carbon to fuse. And so a star like the sun will die, will end its existence at this point. The difference is that a high mass star, because of its tremendous mass and gravity, can actually get the core to collapse and condense down into a size that makes the temperature high enough to get the carbon to begin to fuse. So where an intermediate mass star can't go any further, a high mass star can take it one step further. Of course, to get the carbon to fuse, the core has to shrink and become hotter. The envelope will once again begin to expand. So what started off as a red giant star will then start to swell up to become what we call a red supergiant star. So the onset of carbon fusion at the core is able to extend the life of the star continuously for a period of time following this. Now, the one thing I want you to notice is that we're using these pictures over and over again and just changing the name of the element and the picture color and so forth. So it gets a little bit repetitive. And rather than just doing this over and over again with different pictures, I'm going to switch to a table. And forgive me, tables are always the most boring thing in a PowerPoint you can see, but we'll try to talk our way through it. What I want to show you is the sequence of events that will lead to the end of the life of a high mass star by showing you in particular a set of numbers that goes with one star example. So what I mean by that is this is the set of numbers that go with a star that is 25 times the mass of the sun, or 25 solar masses. And so these are going to be numbers that have been worked out through a supercomputer, through a process that's called a computer model or a stellar model that runs through the physics of this in an accelerated way. So instead of waiting for a star to actually go through its evolutionary sequence, something we would never live long enough to see, we can simulate it inside of a computer and we can see what the results are. So I'm going to show you some numbers that are real numbers that come from a stellar model. Before I do though, the first column is the element that is fusing at the core. The second column is the temperature of the core. And then the third column says duration, and what that means is it's the period of time that the element at the core is fusing. So let me populate it with the numbers here, and we're going to walk through them. The numbers are big numbers, and in science we tend to write big numbers using what's called scientific notation. So I'm going to verbally tell you the numbers that are shown in a shorthand way on the screen here. When the 25 solar mass star forms, like any other star in our universe, of any mass, of any size, it will begin with its composition being mostly hydrogen. The hydrogen is fusing to become the element helium. The temperature at the core for this fusion to occur for this star is 40 million kelvins. So 40 million kelvins, plenty hot enough to get the hydrogen to fuse. This star will fuse all of its hydrogen in its core and run out of hydrogen after only 7 million years. So 7 million years on the main sequence, turning its hydrogen into helium. Once the core becomes helium, of course, helium requires a higher temperature to fuse. Think back or review the previous videos if this confuses you. And helium requiring a higher temperature is, of course, the problem for a low mass star. An intermediate mass star can get the helium to fuse, and a high mass star can as well. The temperature at the core reaches 200 million kelvins, and for another 500,000 years, 500,000 years, this star turns helium at the core into carbon. Now, even though we're saying carbon here, remember that these are carbon nuclei. So this is not solid carbon. This is more like carbon gas at the core of the star. Now, once the carbon at the core develops, carbon will also fuse, but it requires a higher temperature. This star will reach a core temperature of 600 million kelvins, and for an additional 600 years, this core will continue to fuse the carbon into neon. Neon will fuse. When neon fuses, it becomes oxygen. When the oxygen at the core runs out, the oxygen has been turned into silicon. And when the silicon at the core runs out, the silicon has been turned into iron. Each of these requires a higher and higher temperature to get that fusion to occur. Notice the extension of the life of the star is becoming sort of a means to an end. You'll notice that it is, the period of time is becoming less and less and less. Now, it's the last one here that I want to focus on. You'll notice that when the silicon fuses, the fusion of silicon becomes the element iron. Now, the problem with iron is element number 26 on the periodic table. And so what happens is the iron nuclei at the core of the sun will not go through the same process of fusion producing energy that all these previous elements have done prior to it. Let me switch to a picture and I'll show you what I mean. So the star has swollen up to become a red supergiant at this point. And I know it's very difficult to see, but there's a little tiny yellow dot at the center. That little tiny yellow dot is the core of the star. And what I want you to notice is the core has different layers to it. And I'm going to switch to a close-up of just the core here. You'll notice that the core, the very center of the star, has the element iron. Surrounding that is silicon and sulfur turning into iron through fusion. Surrounding that is oxygen turning into silicon. Surrounding that is carbon becoming neon and magnesium. And then above that is helium becoming carbon and oxygen and hydrogen becoming helium. The problem is the core becoming iron is that when you cause the fusion process to occur for iron, it actually takes more energy to get fusion to occur than you get out of the fusion reaction. So what happens is the layer of silicon that is fusing into iron above the iron core is continually adding more and more iron to the core of the star. But what will happen is, at first, the core is less than 1.4 solar masses. And if you recall from the last video, this is a magic number. This number is called the Chandrasekhar limit. And so if the core is less than 1.4 solar masses, then it is the electrons that are part of the core that will hold up the core and resist the crush of gravity. But remember, the magic part of this number is that if you exceed 1.4 solar masses, then the core cannot hold itself up due to gravity. And so what happens is after a period of hours, more and more silicon is turned into iron, which adds to the mass of the iron core. So this number that the core happens to be is getting bigger and bigger and bigger. And after a few hours, what happens is the core eventually exceeds that number of 1.4 solar masses. And when that occurs, what happens is the iron core is going to collapse due to the force of gravity. Now, what I'm about to explain takes place in just a matter of a few seconds. What happens is the core of the star will collapse due to gravity into something very, very small. And we'll talk in a future video about what it becomes. All of these layers that had been previously separated from previous generations of fusion will now also start to come crashing down into this emptiness. The core that was previously this big iron core has been crushed down, and so now you have an empty gap or an empty void that is going to be filled by all of these other elements crashing down. Now, when these elements come crashing down, you get the mixture of what used to be previously separated elements. For instance, silicon now mixes with carbon, and oxygen mixes with helium. And when these elements mix, the fusion process takes over and they begin to fuse into very, very exotic elements. Things like gold or silver or nickel or platinum or uranium. Any element that is higher than number 26 on the periodic table is now being developed or being made inside of the star. The problem, though, is this massive amount of fusion that's happening very, very quickly and very furiously and kind of chaotically. That energy from fusion has to get out. If the energy doesn't get out, the star is going to have a problem. And the issue is the outer layers of the star are not allowing the energy to get out fast enough. So you have this incredible buildup of energy that the layers above it are not allowing to let that energy out in a fast enough fashion. So what happens is the core collapses, an enormous amount of energy is produced, and the layers above it impede that energy from escaping, so the star can't do anything but explode. So what happens is this high mass star will explode, literally blowing itself up and its outer layers into space, following the collapse of the star itself. So the highest mass stars in our universe suffer their final fate when the core of the star collapses. The energy from that collapse is going to be forced to escape at a furious rate, and the escaping of that energy pulls and pushes and just explodes all of those outer layers into space. And what we end up getting is an exploding star called a supernova. Now, the supernova itself is an incredibly energetic thing. It's an explosion that the universe has really nothing that rivals it. And the effects of the supernova are quite interesting and important to you and I. And in our next video, we're going to discuss what happens following the explosive death of a high mass star. We're running a little short of time on this one, so I hope you'll join me in the next one.